Hello everybody, Greg is here. Today I want to tell you a little bit about two new publications in a new journal called Nature Synthesis. I didn't know about this journal before I saw those couple of papers. These two molecules, although they look different, but they have something in common. But I will tell what it is a little bit later. Let's start with the first one, which is a silaketenyl anion. So this is the molecule. Nice to meet you. First of all, why it is special? There's several things. First, double bonds with silicon are rare. I already told that a couple of times in my previous videos. But here we have not only double bond with silicon and not only two electrons that can be a source for further reactions, but we have double bond to carbon, which is double bonded to oxygen. That's why it's called ketenyl. So such molecules were postulated as intermediates in some reactions, but no one ever saw one. And it's always important to show that some species that look exotic or impossible to exist can be isolated in a stable form. It's like finding a new species of an ape or of a whale or something like that. That's why it was published in Nature Synthesis. We can see here the molecular structure, which was identified by X-ray crystallography. Here is a calculated highest occupied molecular orbital showing the electron density majorly above and below silicon-carbon double bond, and shape of the orbital resembles the shape of such orbitals in regular double bonds. The isolation is already a great result, but they were also able to do a reaction with a transition metal, and this reaction very similar to the one I showed for the Sila pyramid with molybdenum hexacarbonyl. It's always important to get new ligands that can be used in many further reactions. This is also a very beautiful picture of the X-ray structure. And before I forget, both in this and of course in the original molecule, there is this potassium surrounded by crown ether. That's just a cation. Every molecule that has negative charge, so you have to have a counter cation. What was not discussed in this paper is a possibility of this resonance structure. I mean, when I see a carbonyl attached to silicon, I always think about carbonyl as a ligand. Same thing as here in molybdenum, right? So you have carbonyls, you have also here you have a carbonyl attached to silicon, but in the original molecule, the possibility of this carbon-oxygen double bond can be, at least partially, as a minor resonance structure, resemble something like that, is not discussed. And this molecule is of a separate interest, like a silicon atom with one bond stabilized by a ligand. I mean, that can be funny. If you remember, I spoke recently about this molecule that looks like a ship from the Star Wars. By the way, May the 4th be with you. So this is again a monovalent tin atom, but in this case it's a radical. And if you put an electron to this radical, you'll get this anion. And that will be a molecule in the same family as this one. Interestingly, there were no reports about neither of them. And of course I would expect that the first molecule of this type would be with a heavier atom, with tin, with germanium, with silicon, like this one. But believe it or not, the first molecule of this type that was published was with carbon. Again, just very recently in the same journal, Nature Synthesis. So what is this molecule? Here, the counter cation, which was potassium in the previous one, it's copper. The anion stays on the carbon, and the ligand that stabilizes this carbon is those lone pair from phosphorus, and phosphorus also the one that makes the single bond. So here, single bond is silicon and ligand is carbonyl, and here, both ligand and the single bond is this phosphine. So let me tell you a little bit more about this molecule. First of all, how it was prepared. I will not tell a lot about synthesis of this precursor, but eventually when you get carbon connected to those two nitrogens by irradiation, you just eliminate a nitrogen gas and you end up with this product. Pretty simple reaction, but to get to this one it took some time. So those arrows here indicate resonance structures which were calculated and showed that they contribute to the overall electronic structure of the molecule. So here you have carbon double bonded with phosphorus, same as here silicon was double bonded with carbon, but here it was the major structure, and here it is not the case. The second structure is this triple bond, which a lone pair from carbon also adds to this bonding situation with phosphorus. But this one is the major one, and it is evident by the electronic structure. So you can see each of those orbitals. A lone pair on carbon, you have another lone pair, like this structure shows, two lone pairs, and it only slightly comes to phosphorus. Here we have a single bond between carbon and phosphorus, and also a contribution of the double bonded structure can be seen. But all of those states exist at once. That's why it's called resonance structure. They also perform several reactions with this beautiful molecule. All of the reactions are with electrophiles. So here we have trimethylsilyl electrophile and chlorine as a counteranion. So counteranion goes with the copper always, and the electrophile goes on the carbon because carbon is negatively charged. So here is just the simple substitution reaction. Trimethylsilyl or triphenylgermanium sit on a carbon instead of copper. Here it is a little bit more complicated. Here we have a methyl electrophile. It adds, but the carbon doesn't hold and the hydrogen migrates from methyl group to the carbon and resulting in a double bond here. When the electrophile is a proton, the resulting carbon dimerizes, forming a double bond between those moieties. And last but not least is again 3-methylsilyl, but instead of chlorine we have a cyanide here, and one 3-methylsilyl goes on the carbon like in this case, but the carbon reacts with the second molecule of 3-methylsilyl cyanide, and the cyanide attaches itself to the carbon, but the carbon and nitrogen switch places. So here nitrogen is terminal, but here it flips and the 3-methylsilyl finds itself on the nitrogen. This is not something very unusual, but still a cool reaction to see in this particular case. So to summarize, we have two new beautiful molecules that were published in a new journal, Nature Synthesis. One is silacatenyl anion and one is copper carbene anion. The countercation in one case is copper. Here I'm not showing it, but it is potassium. The ligand there is crown ether. Here it is a carbene. And although those two molecules are very different, there is at least a small contribution in this case and a major contribution in this case of this interesting monovalent molecule, which were unimaginable before we saw those publications. Thanks a lot. I hope you liked this video. Please like it and subscribe to the channel if you haven't yet. And don't forget to support Ukraine. Have a great day.